Welcome everyone. My name is Chris Friedemann, and I'm the Chief Commercial Officer for NEOS GeoSolutions. Over the next 30 minutes, I'd like to tell you a little bit more about who we are and what we do for our oil and gas company customers around the world. NEOS is a leader in what we have termed multi-measurement interpretation, or MMI. MMI involves the integration and simultaneous interpretation of as many geological, geophysical, geochemical, and petrophysical datasets as possible, including datasets that are accessible in the public domain, resident in our archives or the archives of our clients, or that are newly acquired. NEOS focuses on the downstream aspects of data processing, integration, and interpretation, while relying upon a group of certified third-party airborne acquisition partners to obtain the new measurements we need. We work everywhere from frontier hydrocarbon provinces in which the amount of available G&G and well-controlled data is limited, to data-rich basins in which there might be numerous seismic datasets and well-control points. Because we make use of a data mining technique called predictive analytics, in which we look for subtle patterns and correlations among all the measurements and attributes, we can be especially relevant in plays in which a wide variety of G&G information already exists. NEOS is privately held and backed by a group of well-known investors, including Microsoft founder Bill Gates, Goldman Sachs, Passport Capital, and the Silicon Valley venture capital firm Kleiner Perkins Caulfield and Byers, which made the initial investments in both Amazon and Google. Our customers include several of the world's largest supermajors, a number of well-known independents, and several smaller E&P firms many of you may never have heard of. To date, we focused our efforts in onshore exploration and development settings, although many of the measurements and methods we employ would be equally relevant offshore. I should also note that our methods are relevant in both conventional and unconventional play settings, though our work is focused primarily on acreage high grading and sweet spot detection in unconventional plays over the last several years. A key aspect of predictive analytics involves applying advanced mathematical algorithms to search for subtle patterns and correlations among multiple datasets. Numerous sectors make use of this technique, including financial services, retailing, and the military. Even sports teams from the Oakland Athletics to Real Madrid use predictive analytics to determine which athletes to pursue based on the profiles of those who have been most successful in the past. Predictive analytics is all about attempting to predict future outcomes by analyzing past events. Insurance is a classic MMI example. Each individual presents a different risk profile to the insurer based on a variety of demographic factors, including age, driving history, and location. As many of us can intuit, the grandmother on the left presents a far different risk profile to the insurer compared to the sports car driving young single male on the right. Because the insurer has both demographic information and claims histories from thousands or millions of drivers, it can statistically predict the likely future claims from these two types of drivers and adjust their policy premiums accordingly. We can use a similar methodology in oil and gas exploration. In a conventional play, we can identify the G&G measurements, attributes, and derivatives that correspond to known oil and gas fields, and then search among the datasets to see where this same suite of correlative attributes appears in less explored areas of the play. In an unconventional setting, we can do the same thing, though instead of keying off of and looking for oil and gas fields, we look for the correlative attributes that correspond to the highest producing and perhaps most liquids-rich wells in the play. In other words, the sweet spots. Because we utilize so many different G&G measurements, we can complement and enhance similar methodologies that rely solely upon acoustic data from seismic. For instance, we're able to consider factors below the shale, including basement topography, composition, and faulting, factors within the shale interval itself, like lateral resistivity variations, and factors above the shale, including surface oil seeps and indirect hydrocarbon indicators. Because we're using more data sets, we have more measurements to work with and more subtle correlations among them to mine. In the end, this increases the power and accuracy of our predictions. So let's take a look at some of the measurements we work with and how they are used. I should add that the measurement suite we use on any particular project is tailored to the imaging objectives and operational constraints outlined by our client or clients. For instance, We might leave hyperspectral imaging out in situations where heavy vegetative canopy obscures the surface, or use full tensor gravity gradiometry rather than standard gravimeters in situations where higher levels of precision are needed to demarcate fault planes. In general, however, we typically work with 5 airborne acquired geophysical measurements: magnetic, gravity, radiometric, electromagnetic, and hyperspectral, which we integrate and simultaneously interpret with existing G&G data, including well logs, cores, 2D and 3D seismic, and well production histories. Our interpretive workflow is illustrated by the target. At the first level, we interpret each dataset individually. For instance, we identify faults throughout the geologic column by analyzing magnetic data and a series of filtered magnetic derivatives. At the second level, we interpret several datasets in combination. For instance, we might identify oil seeps and indirect hydrocarbon indicators on the surface by analyzing hyperspectral data, and then tracing the migration paths of these DHIs and IHIs down into the subsurface along faults and lineaments identified using the magnetic data. Lastly, we apply a variety of geostatistical and predictive analytics techniques to quantitatively interpret all relevant G&G measurements, attributes, and derivatives. So let's briefly consider the merits of a multi-measurement approach in shale exploration and development. In the 2D cross-section shown, taken from Argentina's Neuquén Basin, the target Vaca Muerta shale interval is shown here. If we had 3D seismic available, we might be able to extract certain relevant attributes related to faulting, fracture density and orientation, and perhaps brittleness. But how would we begin to move beyond some of these structural and lithological attributes to other information sources that put this shale play in a broader context? For instance, below the shale interval, would seismic, especially if we only had a few 2D lines available, be enough to help us understand the undulations, faulting, or composition of the basement, or the extent of crystalline or salt intrusives, all of which could dramatically affect the thermal maturation regime of the shale horizon above? Within the shale interval itself, would seismic help us understand lateral resistivity variations, which might be indicative of variations in total organic content of the shale, or whether we have gas versus liquid hydrocarbons present? And above the shale, would seismic help us to identify DHIs and IHIs, or geohazards such as shallow gas or abandoned infrastructure that could affect development planning? If you've answered no to some or all of these, then you're making the case for additional measurements to help image above, below, and beyond the shale. The other argument for a multi-measurement approach is operational. Many of the new shale plays, such as the Bashanov in Russia, are simply so large that attempting to image them with seismic, even just coarse 2D seismic lines, will be cost prohibitive. At 3 million square kilometers, the Bashanov is the size of Texas and the Gulf of Mexico combined. Moreover, commissioning a new 2D or 3D acquisition program involves the need to obtain permits to secure access to the land. This process can take a long time, and in many cases leave holes in the survey where topography or recalcitrant landowners refuse to grant access. Moreover, with dozens or hundreds of people on the ground for long periods, the HSE risks begin to mount. Whether we're talking the Bashanov Shale in Russia or the Utica Shale in Ohio, airborne multi-measurement surveys begin to make sense. As a result, NEOS and our clients are beginning to revisit proven airborne geophysical methodologies in this new era of unconventional reservoir exploration, exploitation, and development. Whether the geophysical data is acquired by satellite, fixed-wing aircraft, or helicopter, these airborne measurements, integrated and simultaneously interpreted, are beginning to provide new insights into both emerging and legacy shale plays. Let me read you a quote from the chief geoscientist of one of the world's largest and most highly respected energy companies. Better integration of seismic and non-seismic data sets will be critical to cheaper and faster de-risking of future exploration opportunities. We at NEOS couldn't agree more. Shown here are the deliverables that are typically received by customers who license one of our NEO-Basin multi-measurement libraries. You'll note a rich set of interpretive products associated with regional geology, including the basement, basin margins, lineaments and fault networks, and intrusives. Another set associated with 2D and 3D models, including isopachs, burial depths, and depth to basement maps that are all important in understanding thermal maturation regimes and the impact on gas versus liquids hydrocarbon generation potential. A very unique 3D resistivity voxel that I'll tell you more about later. Maps used to high-grade acreage and to better plan future leasing, drilling, or geophysical programs. And if hyperspectral imaging is used, maps of important geologic and environmental features on the surface. So let's look at some example deliverables from projects we've undertaken around the world. This first one is from the Denver-Julesburg Basin of northeastern Colorado and southeastern Wyoming. I show it to you for two reasons. The first is because it was created with public domain data, and I wanted to highlight that we always start with public domain data, whether Landsat or Aster satellite info or legacy GrabMag data we might get from the USGS or another government agency, which is what is shown here. We do this because it helps jumpstart our interpretation efforts and helps us to better design and plan any new data acquisition in the area. The second reason I show it is it illustrates, quite simply, the power of correlation. There are two large fields in this area of interest, Wattenberg and Silo, which lie just east of the Front Range of the Rocky Mountains, which is depicted by this hot-colored north-south trending area. You'll note that Wattenberg and Silo both sit in gravity lows. Interestingly, they are both also found in areas with magnetic highs. Is it simply coincidence that these two fields share these common geophysical properties? Or might it be that these geophysical properties are indicative of unique depositional, tectonic, or thermal settings that generate hydrocarbons from the Niobrara Shale in this area? Our use of public data often begs the question from clients, well, why can't I just use public data and avoid the time and cost of new airborne acquisition? It's a reasonable question, and depending on the imaging objective, new data acquisition may, in fact, not be necessary. But we wanted to illustrate the trade-off one makes by using legacy versus newly acquired data. What you're looking at here is one particular derivative of magnetic data on the top panel and one particular derivative of gravity data on the bottom panel. In actual fact, we probably work with 8 or so derivatives for each of the magnetic and gravity data sets. The newly acquired data for this particular project in Venango County in northwest Pennsylvania was acquired at 1 kilometer line spacing using fixed-wing aircraft, which is what we typically use on a NEO-Basin survey. You can see that the resolution is pretty high, helping us characterize subtle features and crenulations over this roughly 1,200 square mile area of interest. The black lines are faults that our geoscience team interpreted using all of the gravity and magnetic measurements and derivatives, not just those shown here. We then decimated the newly acquired data back to 5 kilometer and finally 10 kilometer line spacing, which would be more representative of the line spacing associated with most publicly available legacy GrabMag datasets. We then reinterpreted the data to pick faults. You'll see the resolution of the left panels is much worse than those on the right, and the number of interpreted faults is also less. This doesn't mean the left side data is useless, just that it has a set of applications to which it is well suited and others to which it is not. So let's take a look at the interpretation of some newly acquired airborne data, in this case gravity. Gravity data is measuring density variations within the geologic column, with thicker areas containing less dense sediments generally depicted in cool colors and more dense igneous or metamorphic rocks depicted in warm colors. Noting the lower right panel, we're looking deep within California's Ventura Basin, with the basin's margins shown where the purple colors transition into the blue-greens and eventually the hot colors. The lower right panel has been filtered to reflect a depth of investigation of roughly 25 kilometers or nearly 75,000 feet. As we move to the left and then to the upper panels, we're moving up through the geologic column, with the upper left panel reflecting a depth of investigation of approximately 6 kilometers or roughly 20,000 feet. This panel shows the architecture of the sedimentary mini-basins within Ventura. It turns out that there is a significant correlation between oil field locations and the margins of these various mini-basins, which ultimately feeds into our predictive analytics methodology. Another significant correlation exists in the Ventura Basin between the oil fields, shown in the black dots, and the edges of magnetic bodies, which are effectively depicted here by the visual transition from warm to cool colors. Because of the area's significant tectonic activity, remember, we're in the vicinity of a large number of faults, including the San Andreas. We'd expect structure, faults in particular, to play a significant role in both migration and trapping. That's ultimately what we see in the data, with the edges of magnetic bodies accounting for field locations that have contributed 90% of Ventura's historic production. So with just these two data sets, gravity on the prior page and magnetic on this one, we'd have been able to come up with a pretty good assessment of where the oil fields in this structurally controlled basin would be found. If you think one of the basin's longest standing operators knew of these correlations before this survey was undertaken a couple of years ago, you'd be wrong. These datasets and others provided new insights into the exploration potential of a basin that had been in production for nearly 150 years. Magnetic data can also be helpful in identifying intrusives, including the crystalline intrusives shown here. On the left panel, you're looking at deeper magnetic data from roughly 20,000 feet in the western fringe of Argentina's Neuquén Basin. The hot colors running north-south are indicative of some subsurface intrusive complexes associated with the Andes. On the right panel, you're looking at magnetic data that's been filtered to the interval of the target Vaca Muerta shale. The intrusives have spilled out laterally to the east, changing both the lithology and the thermal regime in which exploratory drilling activities are currently taking place. Armed with this knowledge, and that provided by other measurements, the area's supermajor operator has a better sense of the relative prospectivity of the Vaca Muerta. A key aspect of any of our regional neobasin surveys involves model building. Here, we're showing the basics of how we create a 2D cross-section. First, we aggregate whatever information we can to calibrate and constrain our model, including estimates of the magnetic susceptibility and the density of the major stratigraphic horizons in the subsurface, as well as known calibration points, which might be provided by outcrops, 2D or 3D seismic data, or well logs. Next, we run an inversion on the airborne acquired gravity and magnetic data to build a 2D subsurface cross-section, with iterations continuing until the density and magnetic susceptibility of our integrated 2D model fits the actual measurements we've acquired from the air, as well as the constraints provided by the outcrops, the seismic, and the well log information. Here's an actual example from Argentina's Neuquén Basin. This is one of 12 cross-sections we created in a roughly 5,000 square kilometer area of investigation. We had some old 2D seismic lines to work with in some cases, along with a few well control points. Density and magnetic susceptibility estimates came from an analysis of cores and outcrops, along with consultations with local universities and academics. The final 2D subsurface model is shown on the bottom panel, with both crystalline intrusives and faults depicted. The undulating basement, including some basement-to-surface faults, is shown at the bottom in purple. The target reservoir horizon, the Vaca Muerta shale, is depicted closer to the surface, outcropping in some areas, disappearing in others, and varying in thickness, burial depth, and proximity to the basement in others. You'll note in the top panel that the actual airborne data, depicted by the solid lines, matches very well with the integrated density and magnetic susceptibility estimates that are extracted from the models shown. Ultimately, we take the various 2D cross-sections we've built and infill among them using some inversions and mathematical manipulations of the airborne acquired gravity and magnetic data, which has been sampled along 1 kilometer flight lines throughout the entire area of investigation. This allows us to create a 3D model like the one shown on the left, depicting horizons from the basement up through the various reservoir intervals and onto the surface itself. Having built this model, we can extract various horizons from it, including the topography of the basement, shown on the right, but also isopac and burial depth maps of the various intervals of interest. One of the most important measurements NEOS obtains is resistivity. As far as we know, we're the only oilfield services company that is able to obtain deeply penetrating passive source EM resistivity from the air, providing us with the ability to create 3D resistivity voxels on a county scale from roughly 1,000 feet to nearly 12,000 feet below the Earth's surface. Magnetotelluric currents provide the source energy across several different frequency ranges, and therefore enable different depths of investigation. High-frequency signals originate from lightning, in particular ongoing equatorial lightning strikes. Intermediate frequency signals come from ionospheric resonances, and low-frequency signals are generated by variations in the solar wind. We obtain time series, multi-component electrical and magnetic measurements which, following the application of some proprietary signal processing, we convert into the depth domain. We calibrate our airborne acquired data with both resistivity measurements from well logs, if available, and also with resistivity data obtained from sparsely spaced MT ground stations. This methodology lets us create a 3D EM resistivity voxel, which we can interrogate either in cross-section or in depth slices, which is what you're looking at here. This particular example is a depth slice from in and around the Marcellus Shale interval in Tioga County, Pennsylvania. Resistive hotspots are shown in the hot colors, less resistive intervals in the cooler colors. You'll note the yellow circles representing horizontal wells which have been sized to their cumulative first 6 months of production. Vertical wells are depicted in magenta. A quick visual examination suggests a correlation among the resistive bodies and the most productive wells. Production appears to fall off in the less resistive intervals. There are several hypotheses that have been offered up as to what is driving this correlation, but all would be indicative of more productive wells. These include more quartz-rich lithology, which would equate to more frackable wells, localized zones of enhanced TOC, which may have generated more in-situ hydrocarbons, or perhaps we're seeing enhanced thermal maturity in these hotspot areas, which may have allowed more hydrocarbons to be generated out of the available organic material in localized areas. Others have written about a fairly distinct correlation between resistivity and vitrinite reflectance in other shale plays, including the Niobrara, and one could intuit that a similar correlation exists here in the Marcellus. I should point out a quick yeah but area that viewers often ask about. This area, seemingly less resistive but highly productive, is actually impacted by the intersection of several fault boundaries, which we image with magnetic data, proving at some level the value of an integrated multi-measurement approach. Another of the geophysical techniques we use involves an analysis of hyperspectral images. Hyperspectral imaging is based on the premise that every substance on the surface of the Earth absorbs and reflects light in a unique way. We measure these absorption and reflectance points across a portion of the EM spectrum from visible light through thermal infrared. These spectral signatures are analyzed by computers in 3 by 3 meter pixels throughout the area of investigation, which allows us to classify the substance or substances within the pixels. We can use this technique to map different lithologies and outcrops, discriminate between high and low TOC shale intervals, identify oil seeps, or to map potential indirect hydrocarbon indicators. The images you see here are from the Ventura Basin, captured from above a known field called the Ventura Anticline. Starting on the left, you see a false color composite that was acquired over a roughly 1 square mile area above the field. The red colors correspond to vegetation and the gray to exposed ground and soil. On the right, you see that same area, though this time the depiction shows vegetation in green, soil in brown, and any trace quantities of hydrocarbons we can detect in yellow. When we blow up the area in the inset, the yellow hydrocarbon indicators become a little more visible. Though we have a library containing hundreds of spectral signatures, including hydrocarbons, we always ground truth our measurements to be sure they are tuned to the unique geochemistry of every area. So the geoscientist on the inset was deployed to one of the seep-identified areas. Using a handheld device, she noted the spectral signature of the oil seep, located on the right side of the image, and we later compared it to the airborne acquired signature. They are very close, as you can see, and we use this process to calibrate our airborne hyperspectral sensor to look for hydrocarbons associated with the Ventura Basin. If you subscribe to the theory that hydrocarbons often migrate to the surface up faults, then we can use the hyperspectral measurement to identify the surface-based cuts of potential fault systems, and using other geophysical measurements, trace these fault systems down to depth at the reservoir level. In a shale play, analysis of the location and quantity of oil seeps, along with indications from other measurements such as the EM resistivity data, might provide hints as to which portions of a shale play are likely to be more liquids prone. This is another hyperspectral example, this time from Argentina's Neuquén Basin. The yellow oil droplets depict areas with classified oil seeps, determined in a manner as described on the prior slide. The other colors, green, red, and blue, represent several of the alteration minerals we and our oil company client were searching for, under the premise that these alteration minerals may represent indirect indicators of hydrocarbons that have migrated to the surface over time. Our analytic approach was a bit more sophisticated than what is shown here, as we were searching for an even broader array of specific alteration minerals and looking at them not only alone, but also in combination with one another and with the SEEP data. We then combined both the DHI and IHI insights, along with insights derived from other measurements and the 2D and 3D modeling efforts, to identify shale intervals in the subsurface that were likely to be more liquids prone. So let's take a look at how we put the integrated interpretation together using this example of one of our quantitative fusion products. We're looking at data from our Ventura Neobasin survey, with the area in the outline encompassing roughly 1,000 square miles. The colors correspond to our geostatistical assessment of the probability of finding liquid hydrocarbons in this particular geologic horizon, the Pico, the shallowest and most highly developed of the 4 formations we analyzed. Hot colors correspond to a greater probability of finding oil. The black dots are known producing fields. The way this is developed is we identify the series of geological and geophysical measurements that correlate with known fields, though we could also look for correlations with the highest producing wells in an unconventional shale reservoir, for example. The areas that we key off of, in this case the known fields, are known as the training datasets. In this case, we use 3 known areas, indicated by the purple crosshatched boxes, as the training datasets. We always leave out some of the knowns, for example, this billion-barrel field, to see if the predictive analytics method will identify them. In this case, all of the existing fields that we did not use in the training of our algorithms were predicted to have a high occurrence of oil. You'll note that several areas depicted by hot colors do not have any known oil fields. These might become areas for further investigation, geophysical investment, or leasing activity. When we do this, we usually look at more than 100 individual measurements, geophysical attributes, and derivative products throughout the geologic column, but generally we'll find about 20 that correlate with the sweet spots that we're looking for. These measurements could be from anywhere within the geologic column, and among other things might correlate to the distance from mapped faults, high spots in the basement, the intensity of fracture systems in the reservoir interval, and evidence of trace hydrocarbons in the near surface or surface. Once the correlations are established, our algorithms then hunt for similar anomalies elsewhere in the basin, with the hot colors representing areas that share the most similar suite of attributes with the known fields. In the case of Ventura, the analysis becomes even more intriguing as we go deeper in the geologic column, as the number of well penetrations is less and the chances of finding untapped hydrocarbons even higher. I should point out that this sort of analysis is equally applicable in an unconventional shale basin. In this case, We'd normalize for the effects of completions, for instance, the number of frac stages, and look for the combination of measurements that correlate with the highest producing wells, in essence, the sweet spots in the shale. So let's modify the way we looked at the data on the prior slide and also look a bit deeper in the Ventura Basin. The map on the upper left is the same map we were just looking at, only now it's been superimposed on the isopac and structural map for the Pico Formation at the county scale. You'll note that the oil fields in predicted sweet spots sit on structural highs, something that hunts with our intuition of what to expect in a tectonically active basin like this one. On the lower right, we're looking at a deeper formation with fewer well penetrations and a smaller number of historically discovered fields. Once again, you see that the projected high potential areas sit on structural highs and/or are adjacent to fault zones. Seismic acquisition is notoriously difficult to permit in this area, and the costs of a program can be exceptionally high. You can see how this information would let one target 3D seismic programs on the most prospective 5 to 10% of the basin's acreage, which can help to moderate cycle times and future investment levels. Moreover, this information lets one make informed decisions even without the benefit of complete information, something that is usually the norm, not the exception in the E&P business. I wanted to show you a predictive analytics example from a shale play, and we'll do so with this excerpt from our work in the Marcellus. A similar technique as I just described was used to identify and map the potential sweet spots in the Marcellus shale in the area of investigation, which in this case was Tioga County. We analyzed 100 geoscience measurements, attributes, and derivatives over roughly 1,000 square miles and determined that 20 were correlative with the sweet spots. Of the 20, 9 of them, or roughly half, had to do with the structural context of the area of investigation. For example, shale thickness, burial depth, or depth to the basement. 5 of them dealt with plumbing, effectively the fault and fracture networks that allow hydrocarbons to flow within the shale and among man-made hydraulic fracture systems. 3 dealt with the tank, that is the concentration and type of hydrocarbons present, and 3 were associated with halo indicators, effectively direct and indirect hydrocarbon indicators on the surface or in the near surface. One of the other ways we can apply predictive analytics is in a stochastic manner to look at the variability of different parameters that might be used to estimate, for example, gas in place. We can analyze the range of outcomes associated with a particular input variable over the area of investigation, for example, the thickness of the shale interval or the amount of total organic material present, and after aggregating all the input variables and their associated uncertainties, come up with a stochastic prediction of the resulting outcome. On the left side, we looked at these various input variables and uncertainties that feed the gas in place formula, established a threshold of 20 BCF per square mile, and asked the mathematical algorithms to highlight regions within the survey area that were most likely to meet or exceed this 20 BCF threshold. These are depicted in the hot colors. On the right side, we did the same thing, though we increased the threshold by an order of magnitude to 200 BCF per square mile. You can see the amount of acreage at or above this threshold shrinks, but again, there are several areas that pop out as worthy of further investigation and/or geophysical investment, including new seismic acquisition. Again, if time is of the essence and additional information does not become available, these maps could help to inform decision-making about where to explore, lease, or drill. I've listed here some of the questions we are frequently asked, about how long a project takes or how much it might cost, for example, along with the answers to these queries. I won't spend any time verbalizing the answers, as you can pause the slideshow and read both the questions and the answers as you wish. So that does it for the formal presentation. I hope you've learned more about NEOS and our multi-measurement approach and have begun to appreciate how more measurements can be used to provide even richer insights into the subsurface. The airborne nature of the majority of the measurements we use lets us cost-effectively survey large areas, generally without permits. Our certified acquisition vendors know how to get aircraft in and out of virtually any area, as they've been operating in key oil and gas and mining areas for decades. MMI has application in both data-rich and data-poor areas, and in both conventional and unconventional play settings. Predictive analytics plays a key role in what we do, so in many cases, we love having more data to work with when it exists, including seismic. However, when seismic isn't available or doesn't fully cover an area of interest, MMI can be used to supplement or complement it, including to target future seismic investments on the most promising parts of a play. We're excited about what we're doing, and we're delighted that some of the largest oil and gas companies in the world, and some of the smallest and most innovative ones as well, are working with NEOS to help them make better decisions about where to explore, lease, and drill. Thank you very much for your time. To learn more, I suggest you visit the resources page of our website, neosgeo.com.